Now let's start talking about reflective optics. So the difference there is that instead of a lens, we have a mirror. So I'm going to draw that here. And now it looks a lot like a plano concave lens, but we aren't concerned with what's going on here. In fact, big mirrors may have a lot of the glass removed by having a honeycomb shape inside. In fact, the big one on Palomar has a honeycomb shape in the back, and the first time they tried to cast it, the hot glass melted the bolts holding down the parts of the mold that made the honeycombs, and they started coming to the surface, so they had to start over again. But anyway, we have a concave surface, and this time we're concerned with how it reflects light. Now, let's go back to our flat surface. Here is our normal. We're not concerned about what goes on here because this is a totally reflective surface. And here comes our ray of light and strikes the surface at the normal, and that light is going to reflect off. And I mentioned this angle being equal to that angle, which is true, but the angles are actually measured from the normal. So as the angle gets greater compared to the normal, the angle coming in is going to equal what? The angle going out. So a greater angle coming in equals a greater angle coming out. So that light is going to reflect away from the normal when it strikes the flat surface. So what's going to happen when this is a curved surface? Well, let's look at the middle. The light comes, hits the middle, and just simply reflects back. Just like the lens, it went straight through. But if the light is coming in and hits the edge, well, now that surface is angled this way, so our normal is angled that way, and so our light is going to reflect and go in that direction. And likewise, the same thing is going to happen over here. Light coming in and hitting that part of the mirror, the normal is that way, it's going to reflect, and lo and behold, we have those rays of light cross at a point. And just like the lens where light coming in off axis, let's look what happens if it comes in off axis. It's going to come up to something like that. And coming in from this angle, it's going to do something like, getting complex, I'll just draw it there, not a very good drawing there. But anyway, the light is going to focus at different points. So once again, a good test for this is to look at a star where all the light is coming in parallel planes or in parallel rays. And those come in and focus at a point, but the light coming in from an angle is going to have parallel planes or parallel rays coming in from that way. They will focus, coming in from below, they will focus high. Coming in from high, they will focus low. And once again, if we put a piece of card here or something, this thing will form an image. So we have an image formed just exactly like a lens. But what are two big advantages of this? For one, we only have to make one curve. The back of it doesn't mean anything, so it's half the work of making the mirror. But then it does have to be coated with something. Usually they coat them with aluminum and then coat them with something called silicon monoxide to protect the aluminum from the atmosphere, because it would corrode pretty quickly. But anyway, they have to put a reflective surface on it. Now, some amateurs might do that with silver because it's very easy to coat with silver. To coat with aluminum, you have to use extremely high vacuum chambers, and not going to go into that, but at least not now. But nevertheless, it needs to be coated with a reflective material. That's not insurmountable, but we only have to make one surface. The other thing is, there's no chromatic aberration. So we don't have to worry about the different colors focusing at a different point, because that doesn't happen with a reflecting telescope or reflecting optics. Well, except when it comes to a telescope, when you put that eyepiece in there, well, that eyepiece is going to be made with lenses, so we still have to have an eyepiece that corrects for chromatic aberration in the eyepiece, but we don't have to correct for chromatic aberration in the objective mirror. So we had an objective lens, which was the big lens that gathered the light. Here we have an objective mirror. So what complications do we have here? Well, like the lens, if this shape is spherical, I'm going to redraw this because I'm getting all cluttered up here. If this surface is spherical in shape, in other words, If we extend it all the way around, it'll make a perfect sphere. Light coming from the edge is going to focus in one place, but light coming closer to the center is going to focus further out. And this is really exaggerated here, but if the lens is big enough and deep enough, it's actually quite exaggerated. I don't know if I can find a picture, I'll put it up here, but I had a very deeply curved spherical mirror one time, and this is about the size of it. It was actually in a television projector where it had a little tiny television tube here that was extremely bright, had a diagonal mirror here to reflect so that the image was reflected out. So this can work both ways as a projector and as a lens for a telescope. And which is another place we might have to deal with optics and electronics because of electronic projectors, just so you know. But anyway, if I took that mirror by itself and just pointed it at the sun, which is far enough away that the light might as well be infinitely far away, the light from the edge focused like about there, the light from the middle focused like right about there, and if there was a little bit of haziness in the air, I could see a little curvy little cone, basically, of light from that reflecting sun. And so you could very plainly see the spherical aberration in this particular lens. I'm not sure how well the projector worked because the spherical aberration works both ways, so it couldn't focus perfectly on that little TV tube. And then that TV tube was in a diagonal mirror, which caused the light to come out, reflect off that diagonal mirror off in that direction, and would project an image. Never had it actually working because all I had was the lens. I didn't have the rest of the apparatus, and I have no idea where that is now. But anyway, we have spherical aberration to deal with if we have a spherical mirror. So what can we do about that? Well, in early telescopes, what they would do is make this shape a parabola. You've heard of parabolic reflectors. What is a parabola? Let's first draw a circle. Okay, that has one point in the middle we call the focus, and all the parts of the circle are equidistant from that focus. But a related shape, in fact, technically a circle is an ellipse with both foci, plural of focus, in the same place. I'm trying to think of how to make an ellipse. There's different ways, but one easy way is to take two pins. I'm going to draw these a little further apart. Take two pins and put some string around them, and put a pin at this apex here, and just draw that pin around those 2 points. And the length of the string between all the 3 points of the drawing angle will draw what's called an ellipse. We might call it an oval. An oval doesn't need to be perfect. To be an ellipse, it needs to have a specific mathematical function that describes that shape. And you can make one easily with that. There's other ways to mechanically make an ellipse, but I don't want to go into that. But if we get these further and further apart, if we put those two foci really far apart, that ellipse is going to be lots more stretched out. Now, if we put this one infinitely far away, these lines become parallel because they never converge because the focus at that end is infinitely far away. And so now we have what's called a parabola. If we massage this a little further where they never become parallel, then we have a hyperbola. So if they converge, we have an ellipse. If they stay parallel, we have a parabola. But if they diverge, we have a hyperbola. So parallel if it's a parabola, less than parallel, then we have a hyperbola. If they close in, then we have an ellipse. So that's the shape of a parabola. And I'll try to draw this the best I can. I'm kind of flattening the edges and curving it in the middle, but eventually these will become parallel if it's a parabola. Now the advantage of that is that if light hits the edge, let's hit the two edges, and it's going to focus, let's see, it's going to actually focus, this is a very deep parabola, it's going to focus like right about here. So there's the focal point. I'm just kind of drawing this by eyeball. Light from the middle is going to focus at exactly the same place. So no matter where the light hits it, as long as everything is coming in parallel to the axis, it will all focus in exactly one place. We don't have that area of focus that we have with spherical aberration. So a parabola is going to make a better image than a sphere. And of course, in reality, if we make a telescope, we're going to only use a section of that parabola. So let me just kind of redraw this. So we have our parabola. We're only going to use maybe this much of it to make a telescope mirror, and it's going to focus out there. And so we don't have that huge shape that we have to deal with, but there's the idea of a parabolic mirror. But it has its own problems. What happens when the light comes in off axis? So here's our oversized parabola approximation. Light coming in straight on is all going to focus. Let's put it right there, just off the top of my head. There's our focus for light coming in, and all of it focuses at the right place. Ain't that cool? Light coming in from the edge is going to focus in one place, but light coming in toward the middle is going to focus at a different place. So it's great on axis, but off axis, our light from different parts of the mirror does not come to a focus at the same point. So if we look at an image made with a parabolic mirror, in the center, we have a perfect star. I'm using stars because it's a great example to show how the optics work. And of course, we're looking at a terrestrial object. That means around the edges, we're going to have not as good a focus because of the way the mirror works. So light that's coming in on axis is going to focus perfectly, but light that's coming in at an angle is going to focus, but it's going to focus, make these little V shapes, sort of. They call that coma because it sort of looks like little comets. And so that's the problem with a parabolic mirror. So what is the solution to that? Well, two guys by the name of George Ritchie and Henri Chrétien came up with a solution. And that is to make the primary objective mirror, primary and objective mean the same thing on a telescope. So here's our primary mirror. And this shape is actually hyperbolic. So remember the shape, if the lines come in parallel around the focus and back, it's a parabola. But if they're not, it's a hyperbola. So they make this primary mirror hyperbolic in shape. But then they put another mirror here. And they cut a hole in the original. And so the light comes in, reflects off the main mirror, then reflects through a hole in the main mirror. So there's our light coming in on axis. And this particular configuration, the mirror configuration, reflecting to the secondary, then going through a hole in the primary, is called a Cassegrain. But this particular type of Cassegrain, having a hyperbolic primary and a hyperbolic secondary, compensates very well for the coma problem. It's not perfect, and there's what they call secondary coma, I think it is, but it's not as bad as the primary coma. And off axis, it has astigmatism, which means if you have an object that's maybe shaped like a cross, the light coming from here is going to focus differently from the light there. So our light on the different planes is going to be kind of crossing each other in a weird way, where you are able to get maybe that in focus but not this, or maybe this in focus but not that. So I have an astigmatism problem, but it solves most of the coma problem. So it's a much better result than with a simple parabolic mirror. So the way it went when Ellery Hale funded the big telescopes on Mount Wilson and Mount Palomar, a 100-inch telescope on Mount Wilson and a 200-inch or 5-meter telescope on Mount Palomar, George Ritchie, who was building the telescope, wanted to make a Ritchie-Chrétien, but Hale didn't want to risk that because it was a new design and they really didn't know how to test it that well as compared to classical designs. Testing a parabola was very well known, where testing the Ritchie-Chrétien was not very well known, and he was falling behind in the project. And so Hale refused to make a Ritchie-Chrétien. Ritchie quit the project, and they eventually made both of those mirrors as classical paraboloid mirrors. Or was it because Hale thought that Ritchie was making eyes at his wife? Well, there's two stories about that. But anyway, Ritchie quit the project. The end result was those were the last two large telescopes made using paraboloid mirrors, and all other large telescopes made today are Ritchie-Chrétiens. And even amateurs that make their own telescopes often make a Ritchie-Chrétien, although these are weird curves to make. I have access to a 22-inch Ritchie-Chrétien. But anyway, all your big telescopes are now Ritchie-Chrétien designs. Now there are other types of designs that I might as well talk about while I'm at it. Let's get back off of the Cassegrain and back to a simpler design. Remember, we have the problem with spherical aberration. If this primary mirror is spherical, well, Bernard Schmidt solved that, and his best known example is the Ocean-Schmidt telescope on Mount Palomar, which is actually a camera, as I already mentioned. And the difference is there they have a lens in front of the mirror. And in the case of many of them, like the one on Palomar, the lens is actually smaller than the mirror. So I don't know the size of the mirror on the Schmidt on Palomar, but the lens is 48 inches. And it's a simple piece of glass, and is extremely exaggerating its shape, but has a shape something like that. And what that causes is that the light coming in is bent in such a way that light hitting the edges and light coming through toward the middle all focus at the same point. Of course, there are problems with light coming in off axis. I don't know off the top of my head what those problems are exactly, but that's the idea of a Schmidt telescope. And I think typically they will focus, I'm just redrawing this, like about halfway between the mirror and the corrector lens. And so that is where our light is going to focus. And in the case of the telescope on Palomar, they have here, well, there used to be a photographic plate. Now there are electronic sensors there. And this telescope's totally remote controlled now. In fact, can't think of his name now. His last name was Brown, the guy who discovered that thing that might be a planet out beyond Pluto. And so the International Astronomical Union got together and said, shoot, we're going to discover a lot of these. How many planets are we going to have in this solar system? And finally decided to redefine planet. And in the process, Pluto got redefined as a dwarf planet so that we wouldn't end up with thousands of planets in the solar system. Now we have 8, and we have a few dwarf planets such as Pluto, Ceres and Vesta. Those are 2 asteroids which are now considered dwarf planets. And whatever we discover out there in the Kuiper Belt that's big enough to be a planet but not that big will be called a dwarf planet. So anyway, that's the Schmidt telescope on Palomar, but that's the basic idea. And so now there's electronic sensors there instead of a photographic plate. But can you make a Schmidt telescope that you can look through? Of course you can. You just need to put a mirror in here somewhere so that your image, you can put a, that's getting big, so that your image is actually focuses out here where we can put an eyepiece or a camera or whatever we want. So the problem is we have this big obstruction in here. That's a problem with reflecting telescopes, is we often have to have some kind of an obstruction in them to mount a mirror to make the telescope work. In fact, even the Schmidt didn't have a mirror there, but it still had an obstruction. So that obstruction causes problems of its own right. So for example, your typical Newtonian telescope. Let's go to the simplest of our reflecting telescopes, the Newtonian. There's our mirror, which may be any shape you please. Paraboloid, spheroid, whatever. And somewhere around maybe here, guessing just looking at it, is going to be a diagonal mirror. That mirror will probably be elliptical shape, so when we look at it from this direction it looks like a circle. Look at it from that direction it looks like a circle, but if we look at it from that direction it's a ellipse. And that's going to be mounted in a tube of some sort. And there's going to be some kind of a mounting apparatus here and some supports. And so the light comes in past the secondary mirror, hits the primary mirror, focuses on the secondary, and then we have a hole in the side here where we have a mounting apparatus for an eyepiece. And that's called a Newtonian telescope. Guess why? That's one that Newton himself built. So that's only the configuration, has nothing to do with the optics, just like the Cassegrain was if we put a hole in the primary and make this a curved mirror here so that the light reflects back through the primary. It's now a Cassegrain. Either way, we have to have some kind of a support for that secondary mirror. And let's look at some of the problems that causes. So here we are looking down our telescope, and we have a single post holding our secondary mirror. So we look down, we can see the primary mirror, the secondary mirror, they're lined up and probably have an eyepiece right here. Well, what's going to happen? Remember diffraction? We have that wall, and here comes our waves at the wall. And when they hit that wall, some are going to go straight. And I want to modify my drawing a little bit. When I talked about the diffraction in the earlier video, I didn't really do it quite right. The light is going to pass by that post and go in a straight line, but at this diffraction point, we're going to get all new waves. And so notice that these curved waves are going to interfere with the straight ones. So any light coming past that obstruction is going to have an interference pattern, which is going to be where the wave crests come together. We're going to get, well, if we're looking at surface waves, the wave crests come together, we're going to get a bigger wave. Where a crest and a trough come together, it's going to even out. Or in the case of electromagnetic waves, where we have two sections where the positive and negative line up, we're going to get a stronger field. And where a positive and negative are lined up against each other, we're going to get a loss of the field. It's going to cancel out. And so we get these lines where and reinforced because the positive and negative are coming together. In between that, I'll draw that as a little faint, some blue dots in here. In between that where they cancel, and then again where they reinforced, cancel and reinforce. And so the light coming off that edge is going to scatter and create an interference pattern, such as I showed in this image from the previous video. So that's going to affect what we see in the telescope. We're going to get diffraction around the edge of the telescope. We're going to get diffraction around the holder for the secondary mirror, and we're going to get diffraction along this post. And so what's that going to do? When we look at our star in our telescope, we look at a nice bright star, and there's going to be, if we really focus in on it tight with a very powerful eyepiece, that star is going to be a spot with some diffraction rings around it. Those diffraction rings are caused by the outer edge of the telescope and the inner edge of the secondary holder, but we're also going to see a spike go through it. I should have oriented that horizontally. There we go. A spike going through it. That's going to be the diffraction across this post that holds the secondary in there, and that's going to cause its own diffraction. In fact, I'm going to put a link to a video where a woman experimenting with diffraction where she used one of her own hairs. She used a laser and the light hit the hair, and the diffraction caused a pattern to split out that way. So if the obstruction is this way, the diffraction spike will be perpendicular to it. So that's kind of a not very stable way to do it. So let's do this with 3. That's called a spider now. And we have 3 supports in the spider. What's that going to do? Well, I should have left that the way I had it. Here's our star, and we're going to see one spike from that one that's going to go that way. Another spike from that one that's going to go maybe, hope we get these angles right, like that way. And then another one from that one that goes that way. So if we have 3 arms to our spider, we're going to get 3 lines of diffraction, or 6 diffraction spikes across the image. And then if we have 4 supports, a 4 vane spider in this case. We are now going to, I'll just draw it up here. Okay, with a 3-vane spider, we got 6 diffraction spikes. With a 4-vane spider, we're going to get one that goes that way, one that goes that way. Oh, we get fewer spikes with 4 vanes than we do with 3 vanes. How about that? So that's what we're going to have from diffraction. And here's an image from the James Webb Telescope. Now, James Webb Telescope has some interesting diffraction because if we look at it, we have mirrors that are hexagonal in shape. If I can draw a hexagon here, a terrible hexagon. Anyway, the mirrors are hexagonal in shape. There's a hexagon. And each of those edges of those hexagons causes diffraction. So we're going to get 6 spikes from the hexagon because there's 3 different angles. But there's also 2 supports that go up to the secondary. So we get 2 more spikes at different angles. Here's an image from the James Webb Telescope showing all of the diffraction spikes. From the 6 big ones are from the fact that the mirror segments are hexagonal, and the 2 little ones are from the supports for the secondary mirror. So that's what diffraction does for us. Another thing about diffraction is the smaller the aperture, the worse the diffraction is. And so we have a limit to the magnification of a telescope that is directly related to how big it is. The bigger it is, the less the diffractive effects are. And the rule of thumb for astronomical telescopes is that you can get about 50 power per inch of aperture. So while we're looking at different configurations, that's what's going to happen when you have vanes supporting your secondary. There's one very popular telescope that, if you look at what I'm drawing here, you'll see that must be a Schmidt telescope of some sort. In this case, they mount a mirror here, and we go back to our primary mirror, put a hole in it, and so our light comes in, reflects off the secondary through the primary, so it's a Cassegrain. But it has this weird corrector plate, so it's a Schmidt. It's a Cassegrain. It's a Schmidt. It's a Schmidt Cassegrain. And the best known manufacturers of this type of telescope are Celestron and Meade. So that's your Schmidt Cassegrain. What's a great advantage of this? One, it's a Schmidt, so we correct for the spherical aberration. And it's a Cassegrain, and what that does for us is it takes a telescope that would be, take the distance between here and there and add them together. So basically we have a telescope that looks like a shallower mirror that focuses way down here. Let's put our little secondary there, finally to our eyepiece. So the effective focal length is going to be many times the length of the telescope itself. So we measure focal length as an F number. I'll just, little cursive F. And so for what it's worth, as it's coming to my mind, that's about the maximum you can get with a spherical mirror and have a decent image. So I can make a telescope, and as long as the length of the telescope is at least 8 times the diameter of the mirror, I don't really need to worry about spherical aberration. But if I get shorter, now what does getting shorter do for me? Well, it reduces the power, which may be undesirable, but it increases the brightness of the image. So if I want a telescope that makes really bright images, I want to have a short focal length. And they call telescopes that have very short focal lengths and big mirrors light buckets because they gather lots of light and give you a bright image. So if I want to look at a faint object like the Triangulum Galaxy M33, which is pretty nearby, but it's very diffuse, you want a telescope that gathers a lot of light, not much power. You want the light gathering. So you want to take light gathering over power. And the problem we're going to have there is spherical aberration. So we're going to be using a Schmidt or a Ritchie-Stratian once we start getting shorter focal lengths. But what if I want the advantage of the compactness of a short focal length, but the higher power of a longer focal length? And by the way, the power of your telescope is going to be the focal length of the primary mirror divided by the focal length of the eyepiece. If you want the advantage of a long focal length but a short package, the Cassegrain does that for you. The Schmidt Cassegrain also corrects spherical aberration. And while I'm showing that, I'm going to show you a closely related telescope. I'm going to change that part there, and we're going to make our correcting lens a deep, thin piece of glass. They actually call this a meniscus. And this mirror and that lens are nearly symmetrical spherically, or maybe they are symmetrical, so they're the same curve. And then they have the spot, which has a reflective coating, so what we have is a Cassegrain. But the secondary mirror is part of this spherical corrector, and this is called a Maksutov. So if you go around computer people and they're talking about their Mac, what are they talking about? Their Macintosh. But you find a group of astronomers and they're talking about their Macs, they're talking about their Maksutov telescopes. The most famous example of this was probably the Questar, which was a little 3-inch or 3.5-inch that was produced for many years. I don't think they make it anymore, but it was what it was, a little 3-inch telescope with all the advantages and disadvantages of that size. And they may have made an 8-inch, but I don't know. I think they made a bigger one. But as far as I know, the Questar is no longer made. Some amateurs will make Maksutovs. I don't think any professional, well, all professional astronomers use the Ritchie-Stratian now. But anyway, that's the Maksutov. One place where you're likely to see this is on cameras. If you talk about a mirror lens on a camera, that is going to most likely be a Maksutov. So if you see somebody with a camera and you look at that camera lens, there's the lens, and there's a little reflective spot in the middle. It's a big, kind of a big bulky lens. That is probably a Maksutov configuration in there. So why do we need to know about that? Well, because there's sometimes interfacing between optics and electronics. That's why we're going to talk about optoelectronics. So we may have optics that concentrate our light to a point just for detection, and that would be such as like a door opener or something. So we have an LED over here going through a lens, and that's one other thing I need to talk about, what that lens does. That is going to send a column of light across to that's a terrible lens, but I'll try to do a little better here. There's a better lens, and that's going to focus that on a photodiode perhaps, and that's making a beam so that if somebody walks through it, it breaks the beam and detects that something has gotten in there, such as in a garage door opener. Well, there's one other thing I need to mention is what this lens does. It's going to take that LED, and that light coming from the LED is diverging. We want the column of light, so that lens collimates the light. The light is collimated when the rays are parallel. So light coming from a star, that star is so far away that the sphere of light that's emitting from it is coming to us as flat planes, and therefore the rays are parallel, therefore that light is collimated. Or we can take this light here and collimate it, and now we have a straight beam. And then what we need to do here is do the opposite of collimating, which is going to be converge that. So here it diverges, then we want to converge it again, and actually we usually would say we focus the light when we converge it on the photodiode over at the other end. So the light going through there is collimated. And when we talk about laser in the next video, we'll talk about one of the important things about laser light is it's collimated. But we can collimate light with a single lens, and that's how we would do that. Because why? Well, if we don't collimate the light, then the light just spreads out, and the inverse square law says that that light is going to diverge. And if you double the distance, you lose 4 times the energy. The light's going to be hard to detect. But if we collimate it, all the light grabbed by this lens is in that beam, and then we can focus that on the other end. So that is collimating. And so that's one place where we'll encounter optics, is collimating and focusing lenses just to detect something. But then again, there's a lot of imaging done. Imaging is used in, and even mice now have a little camera in there, so imaging is used in a computer mouse. And there are other places where we might deal with imaging. Laser printer has those big lenses in there that focus the image on that plane. So we're going to encounter lenses, and since we are the guy who works with the electronics and there's lenses involved, we probably need to know a little bit about that. And of course, some of what we've learned here will also transfer over to fiber optics when we talk about those. So we may need to collimate light and focus light, or we may need to do imaging. Nevertheless, we may run into optics because we are technicians and we may be working with optoelectronic devices, and so knowing a little bit about optics may be helpful. Maybe I went too deep into telescope optics, but you never know what you're going to run into. So if you found this useful and informative, please give me a like down below, hit that thumbs up. It really helps the channel and helps other people find these videos. And be sure to subscribe and hit that gray bell when you do. For those of you who can't afford to donate, subscribing is a big help, because the more subscribers I get, the more people that YouTube shows these videos to, and the more people will come, and those who can donate will. And of course, a big thank you to my donors and my patrons. I could not make these videos without your support. If you want to help me make these videos and to keep Vocademy free, you can go to patreon.com/Vocademy and pledge your support. And of course, if you want to learn electronics technology, you can go to Vocademy.net and take my free course. And once again, a big thank you to my patrons and my donors. I couldn't do this without your support, and thanks to everyone for watching.